Hi folks, I'm going to spend some time here walking through problems 1 and 2 on the third set of exercises. These are the ones on polynomial regression for daily average gas bill and solder skips for a manufacturing process in semiconductor manufacturing. So let's start with the one on daily average gas bill here. So I've already imported my utilities data set right here. So all of these variables here are now defined in that data set. And the first thing to do is to define the new variable that's daily average gas bill. And if we were to just look, for example, at the different variables in this data set right here, there's one called gas bill and one called billing days. That's telling me the number of days in the month that the company was billing for gas usage on. And then gas bill is just what in dollars the bill was. So if we define daily average gas bill as the ratio of those two quantities, we're now going to be able to compare months with each other when those months had different numbers of days. Okay, so there's that new variable defined, and that will subsequently be the outcome, the response variable in our regression modeling here. I have a small typo here. I'm going to change that to be linear. The first thing is to fit a linear model to this data set. Okay, so just in one stroke here, I'm going to highlight this whole block of code. What am I doing? I'm fitting a straight line for daily average gas bill versus temperature, plotting those two variables, and then putting the fitted values up on that screen. Okay, and so here we are. The open circles are the data points. The closed red circles are the fitted values from the regression. And there's some obvious misfit here that we've talked about as being a textbook example of where you might want to turn to something like polynomial regression to fit the data a little bit better. Okay, so let's now try quadratic and cubic regression models. Okay, so to start off, here's a model with a quadratic term, and we'll do the same thing. Fit the model, plot the data, and superimpose the fitted values all in one stroke here. Okay, great. So now we're getting the quadratic model with that curve. And if we come over here down a little bit, and we fit the model with the cubic term, now in green, we'll see the cubic model. So it becomes, to some extent, a matter of preference here, which of these models you're going to choose. I think it's pretty obvious that the linear model has some flaws with it, and so it's really the running here is between the quadratic and the cubic model. Me personally, I don't see a huge difference in fit between the cubic and the quadratic model. We can flip back and forth between those plots here. There's the quadratic, there's the cubic, so not a big difference. Maybe not much of a fan of the way this cubic model starts to turn up at the end in a visible way. And also, if you're not going to see much of a difference in fit, you might as well go with the simpler model. So for that reason, I chose the quadratic model right here in blue as the one that I'm going to use to produce a prediction interval. Okay, so that's LM2 is the residuals that are going to go into my naive prediction interval. So we start simply by computing the standard deviation of those residuals. Okay, so here it is. And if we just want to eyeball that, what that number is, it's about 0.75. And that looks right. Most points here within 0.75 to 1.5 units of daily average gas bill from the predicted regression line right there. So that certainly looks right. Now let's form our naive prediction interval. So I want to make a prediction at some new temperature that's going to be 50 degrees Fahrenheit. And I'm going to plug that temperature into the coefficients of the linear model. Okay, so here they are. There's the intercept. There's the coefficient on the linear term, and there's the coefficient on the quadratic term. So I'm just going to form my predicted value, my plug-in prediction by hand here. I could use a fancier function in order to do it, but just for illustration's sake, might as well do this here. And what's my predicted value? It's 2.01. So let's make sure that makes sense in the context of the graph over here. Here's 50 degrees Fahrenheit. There's the predicted line, and sure enough, that comes in just above 2. Okay. Now we want to go up and down 2 standard deviations. And again, you could have picked up or down 1 standard deviation, or even some fractional multiple here. I'm just going to pick 2 to get me a relatively conservative naive prediction interval here. Okay. So if I go down 2 standard deviations of the residuals, I'm at about 0.5, and up 2, I'm at about 3.5. Okay. So these two numbers right here would be the endpoints of my naive prediction interval, 0.5 to 3.5. And if I want to calculate the coverage of these intervals to provide some measure of the accuracy, well, I'll first say how many misses low did I have, and so this function right here is saying, all right, for every single residual, let's ask true or false. Was it more than 2 standard deviations above 0? Okay, and that would be that for the residuals here, The 0 line is now given by the regression line here. So if a residual is more than 2 standard deviations above the regression line, this statement right here is going to be true. And now we're just summing up all of the trues. So there's 7 trues right here. And similarly, how many were less than -2 standard deviations below 0? And there are 5 of them. And so if we calculate the miss rate, that's 12 out of 117 data points. That's about 10%. So I'll call my coverage interval a 90% coverage interval. And if we actually want to see the upper and lower bounds of the coverage interval, here we go. We can put the fitted values back on. And now if we scroll down a little bit here, I can put the fitted values plus 2 standard deviations and the fitted values -2 residual standard deviations. And these now form the bounds of our prediction interval. This is a bit of a cognitive sort of illusion here. It looks I think to everybody that looks at this as though these intervals are widening out as you get down here, and they're not. If you actually are careful and measure the vertical distance between, say, these pair of points right here and these pair of points right here, you're going to find it's exactly the same, even though it looks like it's fanning out. Okay, so there you go. We have a 90% coverage interval, rather a 90% prediction interval. And the limits for our temperature 50 would be between 51 cents and $3.51, and that would be the answer to this problem. And again, you may have gotten something slightly different if you use the cubic model, which was totally fine, but I expect, given the visual differences between those two, how minor they were, that the differences in the prediction intervals would also be pretty minor. All right, so that's prediction intervals for polynomial regression. Let's now move on to problem 2, which asked you to look at a model for soldering skips. So these are manufacturing flaws in the manufacturing of circuit boards. And there are 3 predictors in this model. And these are kind of 3 variables that are associated with the nature of the manufacturing task: the opening, the type of solder, and the mask that was used in order to make the circuit boards. So if we start by fitting a model with main effects only here, and we ask for a summary of it, what do you notice? We're going to get a lot of dummy variables here. Okay, so we get an intercept, and then we get dummy variables for a medium and a small opening, suggesting the intercept corresponded to large openings. We get a dummy variable coefficient associated with thin solder, and the other option here would be thick, and that also corresponds to the intercept. And then we've got 4 dummy variable coefficients associated with different types of masks. Okay, so if we actually now go in and ask, what were the other types of masks here? Let me type in for a summary of the data set itself. You're going to notice there were 5 types of masks, 2 types of solders, and 3 types of openings. So for the dummy variables here in this regression model, 3 types of openings, so 2 dummy variables associated with openings. 2 types of solder, so 1 dummy variable associated with solder. And 5 types of masks, corresponding to different sizes here, 1.5, 3, 6, B3, and B6. And that's 5, and so we'll have 4 dummy variables associated with mask. So if you ask, what does the intercept correspond to? It corresponds to the expected response when you've got a large opening, thick solder, and a mask of A1.5. That's the baseline case here. The combination of all 3 of those variables. And then the main effects move you up or down from that baseline right there. All right, so we've got some estimates, and we could bootstrap this if we wanted, for example, to do standard errors. There's all sorts of things we could do, but we're going to talk a little bit more about uncertainty quantification next week. Although you may have been aware of how to do some uncertainty quantification using your first regression course. What I want to focus on right now is the question of whether to include interaction terms in the model. So let's just sort of throw them in there. Consider a model that has all 3 pairwise interactions. So an interaction between solder and mask, an interaction between opening and solder, and then a 3rd set of interactions between opening and mask. All right, so let's fit that model and ask for a summary. And now we have a lot more to look at in this regression output right here. Okay, so I want to call your attention first to one thing here, which is that for opening S and mask A6, we're getting an NA here. No coefficient has been estimated associated with that combination. And the reason why that's happening is because it turned out that if you go back into the original data set, there never were any observations corresponding to this particular combination of a small opening and mask A6. They just didn't do it. And so it makes sense that we couldn't estimate an interaction, sort of a super additive effect of those 2 variables coming in together if we've never seen those two variables together. So that explains that NA right there. Okay? And then let's just to be a little bit specific about interpreting some of these interactions. We've got the same set of main effects as we did before. So the intercept here now is corresponding to the baseline case when we go back to what our model up here was: a large opening, thick solder, and mask A1.5. Here are all the dummy variable coefficients associated with the main effects for the levels of the mask variable, the level of thin solder here, and the two other levels of opening size. And then now here are pairwise interactions between solder type and mask, between opening size and solder type, and between opening size and mask type. Okay, so if we want to be specific here, let's take this interaction right here, small opening and mask B6. What you might notice here is that that's a huge number. That's 14.7 right there. And that's suggesting that this particular combination, if we want to ask what's going on when we have small openings and the mask B6, well, we have the small opening dummy variable, that's there. We have the mask main effect for B6, that's right there. And the sum of those two numbers is a relatively small number, pretty close to 0. But all of a sudden, if we put those two together, there's a huge effect. You get an average number of, an increase in the number of solder skips of something like 14 or 15 right here. And so that's a really important example of an interaction or a synergy here, where those two variables individually don't seem to have very dramatic effects. But together, a small opening with mask B6 seems to be a really bad idea, because you put them together, you get drastically more solder skips. And you have some negative interactions here as well. For example, this one. The medium opening and mask A6, if you go to those main effects, the medium opening has a dummy variable coefficient associated with that, and mask A6 has a big dummy variable coefficient associated with that, so mask A6 doesn't look especially promising right here. However, for whatever reason, we put those two combinations together, the number of solder skips is less than you would expect given the sum of the two main effects, because there's a negative interaction associated with it. And let's just remember, in the context of this problem, positive numbers mean a worse manufacturing process, more solder skips. Negative numbers mean fewer solder skips. Okay, so that's a model with all of the pairwise interactions. Let's do an analysis of variance to try to see if we can attribute the sums of squares to individual variables or combinations or interactions of variables in this model. So that's for an ANOVA, and here we go. And in looking at all these sums of squares, nothing jumps out as being super low. Some jump out as being pretty big, like the opening type and the mask are obviously pretty important here in terms of their contribution to the predictable sums of squares or the predictable variation. If you were going to look at a candidate to think about taking out of the model, it would probably be this one, because it has the lowest contribution to the sums of squares. Let's just see what happens if we do that. So here on line 60 of my script, I'm fitting a model LM3 for skips in terms of opening, solder, and mask. Those are the main effects. And then pairwise interactions between opening and solder and opening and mask, leaving out the interaction between solder and mask that looked like it had a low contribution to the sums of squares right there. Okay, so let's compare the R-squareds. For the original model that I had all the pairwise interactions, R-squared was about 71.7%. If I fit this model that takes out the solder-mask interaction, I get an R-squared that falls by about 2% to 69.5%. So whether that constitutes a significant reduction in R-squared, right now we don't have the tools to be able to answer that question. And so I'm perfectly happy for you to just make a subject area judgment here and using what you know. If you happen to know anything about circuit boards, which I'm not expecting you to do, you may be able to say something. For the rest of us that know nothing at all about circuit board manufacturing, you're just basically expected to take a look at that column and compare it to the other ones and say, well, does it look big, small, modest compared to the rest of these? I might default to leaving this one in because it's not as though it's tiny compared to any of these other contributions. It's still roughly in the same ballpark, even though it is the smallest. But there's certainly a defensible argument here to be said, no, let's just drop that one because it only moves R-squared by 2%. All right, so that's that problem. And just to sum up, what have we done here? We started with a model with main effects only up here on line 47. And then we noticed that we had an R-squared of about 56%. When we added all of the interactions and tried to interpret those carefully, we noticed that we had an R-squared that jumped all the way up to 71% and change, and we had some clearly big interactions here. And by big, I don't mean statistically big in terms of statistical significance. I mean interactions that showed, in practical terms, that there were substantial jumps or reductions in the number of solder skips for particular combinations of these variables. And then we contemplated dropping one of those interactions, specifically the one between solder and mask, because we noticed that it had the lowest contribution to the predictable variation. When we did so, here in the last model, we found that R-squared dropped by 2%. And so, then we have the question of whether to keep that in. And just to preview what's coming a little bit later, we're going to learn a tool called a permutation test that will allow us to assess whether that bump in R-squared of 2% is statistically significant, as opposed to simply making subjective judgments about whether 2% is large or small in the context of the problem.